So, Tom, take it away.
Okay. So I'd like to thank the organizers. I've already learned a lot at this conference. I'm going to be talking about something that's unfamiliar, I think, to all of you, and a lot of it will be controversial. So I'd kind of like you to save your questions till the end, because you'll have a lot of questions. This is a very idiosyncratic personal approach to quantum gravity that I've been developing over quite a few years, though the present formulation of it is fairly recent. It really should have started with some really classic papers from the 1990s that it took me a long time to appreciate. The first of them was written by Ted Jacobson, and I'm going to slightly vary what these people said in their papers. What I think Ted really meant to say is that if you make the assumption that if I give you a solution of Einstein's general relativity, and I look at causal diamonds in that solution, and I make the assumption that every causal diamond is associated with a subsystem of some quantum gravity system whose modular Hamiltonian has an expectation value that's given by the area of the holographic screen divided by 4 times Newton's constant. The holographic screen is the maximal volume d-2 surface on the null boundary of the diamond. Then that assumption almost derives Einstein's equations. It derives Einstein's equations dotted into every null vector in the manifold. Okay? And that derives Einstein's equations up to the cosmological constant. And all you put into that is the Ray-Chowdhury equation, which is just geometry, plus covariant conservation of the stress tensor, plus Unruh's result that if you're basically in a nearly flat space and you accelerate very rapidly, you see a temperature. That's all that goes in. The fact that the cosmological constant doesn't appear should tell us that we shouldn't think about the cosmological constant as an energy density, and I claim that anybody who's really understood ADS-CFT should have known that. Of course, this was written before ADS-CFT, so we should have anticipated that. So the second set of papers were written independently in 1998 by Steve Carlip and Sergei Solodukhin. And what they did was they sort of refined Jacobson's result by they looked only at black holes. In 2021, Carlip Zurek and I realized that their derivation goes through exactly as they wrote it. If instead of just looking at the horizon of a black hole where the geometry doesn't change over the whole horizon, you just look out at the holographic screen of a general causal diamond. So there's a transverse Riemannian geometry on the holographic screen, and in the way Solodukhin says it, if you look at the small fluctuations of the conformal factor of that geometry, the effective theory of those fluctuations is something that had been identified by Belavin, Polyakov, and Zamolodchikov as the hydrodynamics of a conformal field theory in 1+1 dimensions, with a central charge that's proportional to the area over 4 times g Newton. And you can effectively look at that as a kind of another derivation of the assumption that Jacobson made. And furthermore, it gives you a fluctuation formula that's really quite general for the modular Hamiltonian, because 1 + 1 conformal field theory has a universal fluctuation formula. Now, the reason Catherine and I were interested in that was because shortly before that, Catherine and Eric Verlinde had proven a remarkable result, which it turned out had been proven somewhat before that by Jan de Boer and his collaborators, using a beautiful, more general result of Eric Perlmutter's, which is that if you take any example of the ADS-CFT correspondence and look at Ryu-Takeyanagi boundary-anchored causal diamonds and look at the fluctuation of the modular Hamiltonian, it exactly satisfies this fluctuation formula. And then we were a little bit puzzled because another example of a universal fluctuation formula in ADS-CFT is the fluctuation formula for large black holes. And those, of course, have the fluctuation formula of conformal field theories in higher dimensions. And we thought about that for a little while, and you can understand that in terms of the tensor network model of conformal field theories, and I'll explain that to you a little bit later. So the way I want you to think about this is to think about this as telling us that what Einstein's equations are like the Navier-Stokes equations of quantum gravity. If somebody gives you a solution of Einstein's equations, you should say, oh, I should look for a quantum mechanical system which has all of these subsystems given by the causal diamonds in this geometry. And I've been told something about the density matrices of all of these subsystems in some particular state. How should I think about that state? Well, you should think about that state the way we think about the vacuum in quantum field theory. It's what I call the empty diamond state corresponding to that geometry. And I'll tell you a little bit more later about how you think about diamonds that have things in them. Okay. Now, how do we now think about the quantum dynamics of this quantum system? So quantum dynamics has to do with time evolution. To think about time evolution, it took me a while to figure this out, but again, you can take it from quantum field theory, and I have to apologize, Leonardo, the right clue is from algebraic quantum field theory. There's a thing you can do with causal diamonds, which is very useful, which is to think about a big causal diamond as being made up by nesting smaller causal diamonds. So you can take, in any space-time, you can take a nesting that starts from a very small diamond in the past or a very small diamond in the future and nest up, making time steps of order the Planck time in each direction. And if your space-time has a time reflection symmetry, you can also nest out from the symmetry point. What did I do? Uh-oh. Oh, I see. Hit the wrong button. Okay. So, now, in quantum field theory, if I give you a picture like this, and I give you two diamonds with a little bit of time between them, there's something called half-sided modular flow. Quantum field theory does not have density matrices for diamonds because the operator algebra of a diamond is what's called a type 3-1 von Neumann algebra. Those of you who don't know what that is, believe me, they don't have density matrices, but they have these things called modular operators that play a lot of the roles of a density matrix, and you can construct from the modular operator a one parameter set of unitary operators that maps the local operator algebra into itself. Okay? And that's called, for the case where I take the nested, there we go, the nested diamonds like this, and I take the inverse of the modular flow up through the small diamond, and then do the positive modular flow in that last little bit of the of the big diamond, I get time evolution in that little strip between the two diamonds. So these are flows that exactly preserve causality. So now, if I've given you a prescription for what the density matrix is, I'm claiming that I have, at least inside of diamonds, a notion of time evolution. It's not the global time evolution that we're used to talking about in quantum field theory, where I give you the Hamiltonian, but it's the analog of the modular time evolution inside of individual causal diamonds. Okay? Now, I told you the fundamental principle here is that finite area diamonds correspond to finite entropy. Those of you who know about operator algebra theory know that that doesn't mean finite dimensional Hilbert space. However, for 25 years or more, Willy Fischler and I have always assumed that it meant finite dimensional Hilbert space. And various people have yelled at us about that. I've always believed that the reason for that, and I'll tell you why later, is that there's no way on Earth that we're ever going to do a measurement that will distinguish even between the possible finite dimensional models of what's going on inside a finite area causal diamond. So making believe that we can make an infinite dimensional model that we'll ever test is just kind of hubris of a kind that we should not indulge in. Okay. So how do I think about what's going on here? We've got this background geometry which defines the hydrodynamics of our quantum system. It also defines a space of time-like geodesics. So the way we should think about the quantum dynamics is to think about a Hilbert bundle over the space of time-like geodesics. The space of time-like geodesics is not compact. It includes null geodesics as limit points. And over each of those geodesics, we have at least a partial notion of time evolution inside of causal diamonds for finite intervals of proper time. And so we've got the beginning of a theory of time evolution, which is manifestly non-background independent. So we've had this fantasy that we were going to have a background independent theory of quantum gravity, and then we've had, since Juan Maldacena, and really since perturbative string theory, we've had this evidence that we don't have a theory of quantum gravity that's background independent. We could have imagined, because perturbative string theory was only perturbative, that was just, oh, we don't know the full theory. ADS-CFT, we've got all of these independent unitary models that have nothing to do with each other for the most part. At best, they're connected by renormalization group flows, okay? They're different models of quantum gravity. They're different. They're different backgrounds, different physics, different models. So what this says is that every background is different. The reason Einstein's equations look the same is the same reason that the Navier-Stokes equation looks the same, even though every material is different. Okay. Now another word that I like to use now that friends of mine like Daniel Harlow have taught it to me, is that what this Hilbert bundle formulation is it's a non-isometric encoding of the information in a theory of quantum gravity into one quantum gravity Hilbert space. What is that Hilbert space? Well, if I take any one of these geodesics and think about its time evolution from time minus infinity to infinity, assuming that I can extrapolate from minus infinity to infinity, at least in the examples we know, like Minkowski space or anti-de Sitter space, that should be the whole Hilbert space. And we've got that multiply described over all of these different geodesics, and that's what I mean by a non-isometric encoding. All of these are Hilbert spaces. There's no negative metric stuff, and there are just multiple descriptions. Now, why do we need those? We need those because naturally our time evolution is described locally in individual causal diamonds. And in an individual causal diamond, I can't tell you what's going on outside of that causal diamond. But my friend over there on another geodesic, who I haven't yet seen, can tell me what's going to hit me sometime later. So I need his information in order to know what's going on in my full Hilbert space, okay? So there's a principle that I know how to formulate, but not in an efficient way, called the quantum principle of relativity, that forms a connection on this bundle of Hilbert spaces. And the principle is very simple to state, but despite 20-odd years of thinking about it, I have not been able to come up with an efficient way to turn this into equations. And the principle says the following thing. If I take any pair of diamonds, they could be diamonds along the same trajectory, the same geodesic, or a pair of diamonds along two different geodesics. They will sometimes have an overlap region. Now, despite what the two-dimensional pictures show you, that overlap region is not a causal diamond, but except in 2 dimensions. But in general, it's got a maximal size causal diamond inside of it. The natural hypothesis is that that maximal size causal diamond should be identified as a tensor factor in the Hilbert space of this diamond and also in the Hilbert space of that diamond. And it's a tensor factor of the same dimension. This is a place where it's really important that I'm assuming the Hilbert spaces are of finite dimension, because otherwise you don't know what you're talking about when you say tensor factors. And now the dynamics on diamond 1 and diamond 2 will assign that tensor factor to different density matrices. The quantum principle of relativity says that for any pair of diamonds, the density matrices on the overlap should have the same entanglement spectrum. Okay? That's shared quantum information. What the bases are in those 2 different Hilbert spaces, those are different. So you should be able to do unitary transformations that relate one to the other, but the spectrum of the density matrix should be the same. Okay.
But this is supposed to lead to a connection on a Hilbert bundle over what space?
Space of timelike geodesics
You have a
on the
Hilbert bundle
background.
over the space of all timelike geodesics, and you want a connection on that space.
Right.
On that bundle.
On that bundle.
And so, do we know what the bundle is? I mean, is the space of all timelike geodesics, is it contractible? What kind of space is it?
That I have to defer to
The
your
bundle is
greater.
probably trivializable. I mean,
Yeah.
given a bundle.
Yeah, I mean, it may depend a little bit on what your manifold is, because these manifolds in general are going to have compact factors.
Let's see, so these are complete geodesics, they go on forever?
Yep. Yep.
So you have the spaceable geodesics, you have somehow a Hilbert bundle over that, and you want a connection on that. And you're saying that connection should follow from these ones.
Is it a flat connection? I mean, if we identify the fibers at two different geodesics, does it depend on the path I take?
No, I don't think so.
So it should trivialize.
It should trivialize.
So that I can uniquely identify.
Right.
That's what you wanted, a single Hilbert space.
That's what I want, yeah.
But how did you have a Hilbert space attached to the causal diamonds?
Sorry?
You had a Hilbert space, you have a Hilbert space attached to each complete timelike geodesic.
Yeah,
But
I've
also
told
had
you
a-
what the dimension of the Hilbert space is. Now, I have, which I'm not going to tell you about today, I have a personal description of what I think the degrees of freedom are, certain fermion operators and so on and so forth. It's too much to talk about today, and I won't get to talk about symmetries, which are the main purpose of this workshop, if I tell you about that.
But following up on Dan's question, you have a bundle over the space of time-like geodesics, and from that, you're supposed to get a bundle over the causal diamond? Or
Yeah.
associated to it, sorry, a Hilbert space associated to a causal diamond, is that right?
I've got, yeah, in addition to the space of time like geodesics, for each geodesic, I have to give you a nesting of intervals with Planck time separation.
Okay, so there's some more data there.
There's some
We'll
more
ask you.
data, yeah, to give you the causal diamond. Okay, so now let's get to symmetries. So even if the hydrodynamic spacetime has isometries, those isometries don't generically act on geodesics, and they certainly don't act on causal diamonds, okay? So as I said, the time evolution in a causal diamond is modular flow. So even if there's a global time-like killing vector, time evolution in the causal diamond is not that time-like Hamiltonian. In fact, there's a theorem in quantum field theory that says if you have a time-independent Hamiltonian and exact causality, which I've imposed here, then your operator algebras for local diamonds have to be type 3. Okay, I have finite dimensional local algebras. The only way you can do that is with time-dependent Hamiltonians. Okay, so we don't have local symmetries in the local diamonds. Okay, this is now my current version of the no symmetries in quantum gravity theorem. Okay, same thing is true for internal symmetries. The symmetries in a causal diamond, obviously, there's going to be stuff going on the boundary. Do I know whether that's because they're actually symmetries and they're just coupled to non-singlet stuff on the boundary, like a gauge symmetry would be? Or is it because the symmetry is fundamentally broken? No way to tell from the local formulation. The only way we can have a symmetry in this kind of setup is if it's an asymptotic symmetry of the time goes to infinity behavior. Again, if you think from the point of view of effective field theory, the modular Hamiltonian that I was talking about, as I told you, it's something that has to do with what's going on the very boundary of causal diamonds. If you think in quantum field theory, that's the place where quantum field theory breaks down. That's where all the singularities in quantum field theory commutators are, all the problems with firewalls, all of this nonsense that people have run into when trying to think about black holes happens on those boundaries, okay? So there's no reason for this formalism to have any global symmetries. So asymptotic symmetries, what one might hope for, and what we basically know is true in asymptotically anti-de Sitter spacetime. So as proper time goes to infinity, we get one Hilbert space along a geodesic. Now what happens to the Hilbert space as we go along that geodesic? Well, this is something that has to be examined case by case. The case we know about, the case where we really understand what's going on, more or less, as Leonardo showed us this morning, we don't even understand that case completely, but we understand it pretty well. The way I would tell you to think about it is the quantum principle of relativity relates what's going on one geodesic to what's going on another geodesic. So in principle, if there are space-time transformations that are mapping one geodesic into another, and they're effectively telling you there's an equivalence of quantum information between those different geodesics, then those should become asymptotic symmetries. Now, the way that seems to work in ADS-CFT is the following. Once you get to something of order the anti-de Sitter radius, these embedding maps that I told you about that are the analogs of modular flow, we have a much better picture of what those are. Because the way you have to think about this, once you get to something of order the ADS radius, is something that we were taught to do by first Brian Swingle, then Anna Mary and Daniel and collaborators. And it's called the error-correcting code or tensor network picture of anti-de Sitter space. So I want you to think of what I've told you about before in the anti-de Sitter case as what's going on at scales much smaller than the ADS radius. And as I approach the ADS radius, these embedding maps should be thought of as something that many of you may not know about, but there's a very beautiful thing called the Tensor Network Renormalization Group that was invented by Evenbly and Vidal and actually carried out for simple conformal field theories in 1+1 dimensions, which is exactly implementing the renormalization group by embedding maps of nodes of a tensor network into nearby nodes in the bigger shells of the same tensor network. And Willy Fischler and I, in 2016, interpreted those embedding maps as the time evolution along timelike geodesics in anti-de Sitter space. So if I take a tensor network, you usually think of it as centered around a particular point in a time-like, a space-like slice along in hyperbolic space. That center point is the center of some time-like geodesic. Each shell of the tensor network is the base of a causal diamond of some fixed proper time in anti-de Sitter space, and the Evenbly-Vidal tensor network renormalization group should be thought of as the time evolution along that time-like geodesic. Now, actually carrying out their renormalization program for any realistic ADS-CFT model is a total fantasy. Nobody's ever going to do it, but the conceptual idea is very clear. Okay, and in the happy paper, if I may call it that, Daniel, we even know how to do this in a way that's invariant under discrete subgroups of the translation group in hyperbolic space. And so it's in a way that will kind of guarantee the quantum principle of relativity, at least discretely, and in a way that's sort of going to make sure that the continuous symmetries of ADS space are implemented on the boundary. So I think it's pretty clear, and we know, of course, because quantum field theory does implement the global symmetries that we know are there. We know that asymptotic symmetries are going to exist in the case of negative cosmological constant. I'm just trying to put that in the context of the general framework that I'm telling you about. Okay. Now, vanishing cosmological constant. Now, here's the place where a lot of you are going to get upset.
Wait, Tom, before we go there, 2 slides ago, I think you said you had an argument for no global symmetries in quantum gravity based on causal diamonds.
Yeah,
That argument didn't make any use of black holes, is that correct?
that's correct.
So it's independent of black holes, it's
Yeah.
just using the physics of causal diamonds.
Yeah. And this particular way of thinking about quantum gravity, which you cannot buy if you don't want. So you might think that black holes are a more robust way of...
No, I'm just wondering what the logic is used. I've thought that black holes are central to that. You're saying no.
Okay. So now let's talk about vanishing cosmological constant. Now, perturbative string theory has made us think that there's an S matrix in quantum gravity. And I believed this for a long, long time. But we always knew there was a really serious problem in 4 space-time dimensions, even more serious problem in 3 space-time dimensions. I always used to think that Fadeev and Kulish had solved the problem in 4 space-time dimensions. Recently, Wald and his collaborators have cast doubt on that, and a lot of people I know agree with them. But in fact, there are lots of really serious arguments coming from both the positive and negative cosmological constant limits that there can't really be non-perturbatively an S matrix in any number of space-time dimensions. And basically, these have to do with the fact that both from positive and negative cosmological constant, the entropy of empty Minkowski space looks like it's infinite. So in the de Sitter case, that's obvious, should be obvious to all of you. The de Sitter entropy goes like the radius squared in the 0 cosmological constant limit that goes to infinity. You might say, well, we don't understand de Sitter space, so why should I believe that argument? And I'm totally on board with that. But the same thing is true for negative cosmological constant. So the original papers that proposed getting the S matrix from ADS-CFT correlators were written by Polchinski and Susskind. And Polchinski and Susskind identified what they called the arena. And the arena was a causal diamond in anti-de Sitter space that was smaller, considerably smaller, than the anti-de Sitter radius. And now I'd like you to consider that region from the point of view of the tensor network picture of anti-de Sitter space. And now think about that region in the tensor network in just about any state you can think of in the anti-de Sitter, in the conformal field theory, the vacuum, or some state where I've acted on the vacuum with some operators or whatever. That state is, that region is entangled with the entire CFT, okay? Page's theorem tells us that it's a very, very, very high entropy state. I'm not going to claim it's infinite entropy, but it's a very high entropy state. And so what we must be doing when we're making the Polchinski-Susskind operators that probe that region and make what we call S-matrix elements is we must be somehow lowering the entropy of that state, okay? Inserting local perturbations into the arena is lowering the entropy of the Minkowski vacuum. That's exactly what the Schwarzschild-de Sitter black hole entropy formula tells you, okay? So the idea that quantum gravity in Minkowski space is built on Fock space, which has a unique zero energy state, that can't be right, okay? And the problem in 4 dimensions is just the limiting extreme version of that. In 4 dimensions, the S-matrix doesn't even exist in perturbation theory. But in any number of dimensions, if you go to high enough order in perturbation theory, there are matrix elements where I scatter 2 gravitons into 2 gravitons with finite momenta, but I also emit 15,000 gravitons with energy below any cutoff that you might like, okay? Where do those amplitudes come from in ADS-CFT? Well, the place they come from in ADS-CFT is you take connected correlators in conformal field theory, and you make 4 of them into Polchinski-Susskind operators that go into the arena, and you make 15,000 of them into operators that go off into all the other remote places in anti-de Sitter space, and you think about Witten diagrams where there is graviton exchange between all those things that went off someplace else in anti-de Sitter space and the operators that went into the arena. And some superposition of all of those amplitudes is what's going to lead to the soft graviton states. Now, somebody has to prove that as the number of soft gravitons goes to infinity, that defines a normalizable state in Fock space. Nobody's ever done that, okay? The same thing happens in perturbative string theory. Raju and collaborators showed that when you do calculations in perturbative string theory with many, many soft legs, perturbative string theory breaks down. There's just no evidence, there's absolutely lots of evidence in high dimensions that S-matrix elements in Fock space are completely finite. Everything's okay, we don't have the infrared problems of low dimensions, but there's zero evidence that the S-matrix itself is a unitary operator in Fock space, okay? And my collaborators and I invented a non-perturbative formulation of string theory in Minkowski space. Exactly the same kind of problems happen there. So I think the question of asymptotic symmetries in Minkowski space has to be preceded, if we want to answer it non-perturbatively, by the question of what is the space of asymptotic states in Minkowski space, and questions like, does the Bondi-Metzner-Sachs algebra act on that, or what algebra does act on it? I've made a proposal some years ago. There's an algebra, a supersymmetric generalization of the Bondi-Metzner-Sachs algebra that was invented by Iwata, Gibbons, and Shaw. And I proposed a version of that that might be the right algebra to think about representations of. I was not able to prove that the representation space that I suggested defines a separable Hilbert space, and I can't prove that the formalism that I've told you about today gives rise to a Lorentz invariant scattering amplitude on that space. But I think those are the questions that have to be answered. Now, let me finally get to the irritating case of de Sitter space. De Sitter space with spherical spatial sections is a space everyone agrees has finite entropy. Willy Fischler and I independently in 2000 suggested that it be described by a finite dimensional Hilbert space. We've been working on that for many years. One of the most interesting, to my mind, things to come out of that was this idea that localized objects in de Sitter space are constrained states of the vacuum is the maximal entropy state. It's not the maximal entropy density matrix on the Hilbert space that we now know, or I now know from Carlip and Solodukhin, is this density matrix given by conformal field theory, but it's the maximal entropy that quantum gravity allows on that Hilbert space. And a young, he's no longer young, but at the time was young, a young postdoc named Tomeo Fio, who had been a Rutgers student, suggested a matrix model that reproduced the black hole entropy formula. And we've been working with that ever since. And so I think that's a good start, but it leads to really disturbing consequences. I'm going to skip over this really interesting work of Collier, Eberhard, and Mullman. I can tell you about it if people ask me questions, because I want to tell you about the really disturbing conclusions that we've come to thinking about de Sitter space, because we really do seem to live in an asymptotically de Sitter universe. So this is a universe which has a finite entropy, but there's a question of how much of the quantum information in that universe is accessible to any kind of local observer, okay? So there's a very old argument. It goes back at least to the 1980s. That's when I heard it from 't Hooft. I think it's much older than that. That if you take quantum field theory in a region, and you look at all the states in quantum field theory, and you just calculate the expectation value of the stress tensor in most of those states, the gravitational back reaction creates a black hole that's bigger than the region. So it doesn't make sense to include those states in quantum gravity. And if you throw those states out, you even get less entropy than the entropy associated with the boundary area. It scales in 4 dimensions like the 3/4 power of the area. Now, I didn't really know what to think about this result until Cohen, Kaplan, and Nelson wrote a beautiful paper in 1998 in which they showed that even if you leave all of those states out of quantum field theory, you don't disturb the agreement between quantum field theory and experiment at all, okay? So we always say, oh, quantum field theory is such a good theory, we have to be in very good agreement with it, but in a causal diamond, most of quantum field theory is probably wrong, okay? On the other hand, von Neumann long ago taught us how to think about detectors. And the way you have to think about detectors in quantum mechanics is if you've got a system that you want to measure that has a certain number of qubits that you want to measure, your detector has to have, for every qubit you want to measure, a semi-classical qubit that can be entangled with the qubit in the system you're detecting. A semi-classical qubit is a subsystem of your detector that has a lot of quantum states such that its fluctuations are very small and its histories decohere. And that's usually characterized by some large integer n, which is kind of the number of atoms in the subsystem. And the fluctuations go like 1 over n or 1 over square root of n, and the decoherence of the histories is exponentially small in n. And for ordinary detectors, it's absolutely trivial to satisfy this. But if you've got many fewer degrees of freedom in quantum field theory in your system than the number of degrees of freedom in the system you'd like to measure, you're never going to be able to detect most of the quantum information in the system. And so whatever theory we make, we're never going to be able to test it with complete accuracy, even if the real theory is finite dimensional, okay? Because the only way we know how to make mathematical theories of detectors with all these moving parts that have semi-classical qubits is using quantum field theory. That's the only kind of mathematical system that has anything to do with the real world that we know how to make up. And quantum field theory put together with gravity just doesn't have enough states to detect what's going on in a finite universe. So, our bad luck. Thank you very much.